Hello everybody, my name is Kurt Munson. I'm the engineering manager here with HBM nCode. This is part of our continuing webinar series on engineering aspects of durability, fatigue, nCode software uses, and such. Today our topic is called Benefits of Load Reconstruction, and we're going to look over the next, say, 45 minutes or so at how we can think about structural analysis, understanding strain response, stress and strain response in a structure, and also ultimately trying to work back to the loads that would have caused that structural response. And we'll see why loads are useful in a design sense in a way that maybe strain may have a limited shelf life. Loads offer us a lot of flexibility in terms of looking at next generation usage and such. So as was mentioned just a minute ago, I'm going to run through some technical aspects of what we're looking for today. I'll also have a software demonstration in just a little bit, so we'll be kind of split between some PowerPoint slides and also technical demonstration of the nCode software, how this load reconstruction works inside it. And then we'll have an opportunity for questions and answers at the very end. So if you have questions along the way, please indicate those to us through the WebEx Q&A or chat panels, and I'll do my best to answer those questions towards the end of our presentation. So the agenda. Every meeting is supposed to start with an agenda. I once learned that 3 parts of a meeting are: number 1, talk about what you're going to talk about. Second part is talk about it. And then third part is remind people what you talked about. So what are we here to talk about? First off, what is load reconstruction? Key topic for the day is load reconstruction. So I need to define what that is. We also need to look at item number 2 here, which is what is the value of strain or stress response in structural analysis. Third topic for the day is traditionally how do we measure loads? How do we come up with an estimate of loads in situ? So from service loading, from flights, from vibration, from usage, whatever it is, proving ground, road loads. What are typical approaches to measuring loads such that we can then analytically look at structural response? And then lastly, we're going to look at a newer approach. So largely what I'm trying to bring to your attention today is as analysis capabilities or processing functions have increased over the years, this has afforded us some new capabilities for predicting loads. And really that's what we call loads reconstruction. So this is our basic backbone of what we're doing today, these 4 things. So let's just take a quick look, delve into the first, and look at what is load reconstruction. Okay, so first off, before we even define what load reconstruction means, I just want to talk a little bit about what does load mean, right? So, you know, this is a plot here of the cost of making changes, right? So what this really is trying to show is that the more we can learn up front about a design, the cheaper it is to make changes around it. So this really requires a good understanding of loads. So if we can understand loads earlier in a process, the earlier the better. The cheaper it is for us to make changes in the development process. So loads, of course, have enduring value. Structural response, like stress or strain, has value, but maybe not quite as enduring value as loads data does. Now, strain or stress data tells us about the structural response, and that's awesome. So we can learn, say, for this car body and weight, we can learn all kinds of interesting things about what are local stresses and strains and such, and that tells us a lot about this design. Now the challenge is that with iterations on this design or new designs in the future, strains may have limited value because strains are typically extremely focused on local geometries and methods of loading and such, and those kind of things then, as a result, then strains may not tell us much about what we're going to learn with our next design, or how do we even start our next design. So loads, though, on the other hand, have an enduring value, and that is that, typically speaking, if we look at, say, any component, a car body, a rocket ship, part of your phone, whatever it is, typically speaking, the next generation of that design will probably have to endure the same type of loading that the previous one did. And so in that respect, then load is kind of a non-geometric sensitive parameter. It's an input, whereas the strain is a response. So the cool thing here is that if we can think about loads more frequently, then it helps us understand design changes and new designs as well. Lastly, another way to look at this is the last bullet point, and that is that as we work to lightweight things, everything is all about lightweighting these days. I didn't even know this was a verb until a couple years ago. Now it's just absolutely everywhere. Lightweighting, lightweighting, lightweighting. Lightweighting changes strain. It doesn't change load. In other words, if we can understand load, then we can use that load to see how effective our lightweighting is, whereas strains from a structure, the structural response, may not help us much, right? They'll help us understand a current design, but not the next design. So clearly, understanding load is really important here as we move from one design iteration to the next. So let's think about how loads and strains are related, or loads and stresses. Test engineers talk about strains a lot because they use strain gauges. FE analysts talk about stress a lot because that's typically what they look at when they look at pretty pictures on a contour plot. So I'm going to use the terms stress and strain just interchangeably today during this presentation. Typically speaking, if you're doing finite element analysis, typically speaking, you have the route that's shown up at the top here, and that is that an in-service loading history that we apply to a finite element model tells us local structural response. So we can figure out stress and strain response based on some analytical approach. Now that's good. That's a traditional approach. We can say, if we understand loading, we can figure out what the structural response is. That's good. But if you think about this as a mathematical problem, we can look at this backwards now. We can actually turn this around. We can think about this as, why don't we use strain or stress response that we know, so measured stresses or strains, why don't we use that to work backwards to get to the loads that would have caused them, okay? So the key thing here is this strain gauge matrix that I'm calling A. So think about this green rectangle here at the bottom. You're going to see this a lot today. So this is one of the pictures worth 1,000 words kind of images to keep in mind today. This strain matrix A is really what finite element analysis tells us, right? FEA, if we can get a good mesh and a good converged solution, that tells us how load becomes stress or how load becomes strain. We can work backwards through that then to figure out how, for strains that happened, what were the loads that caused them, which means then we can calculate this gray box in the lower left corner, this in-service loading history. That's the load data that has enduring value, right, that we just talked about with the previous example. Load data has enduring value. So we're going to look today at, technically speaking, mathematically speaking, and also in software, how do we actually perform this calculation at the bottom, which is working from measured strains in a finite element model that makes sense to get back to the loading that caused those strains. And we can use those then for future design work. So loading has enduring value. Now, traditionally, there are these load transducers that people have been using, and these are awesome things. Often these are custom built. They're very sensitive and highly linear, and often they mean we have to replace a part with one of these load cells or torque cells or something like that. So very precise, great linearity, but they require replacement of a part. And the downside of that is it may be that replacing a part may change mass, may change stiffness, may change dynamic characteristics, may be expensive, may be, actually, to be honest, may be very, very hard to do in terms of some geometries. So this is a great approach that's been used for a long time and will continue to be used in the future. What I'm talking about today is an additional tool in your engineering toolbox, which is this thing called load reconstruction. So to introduce the concept of mathematical how does load reconstruction, let's look first at how a traditional force transducer works. So imagine you're building this little beam, okay? So you have the beam and bending. This takes you back to your college days where everything was a beam and bending or a beam under axial loading. You can imagine if we had a strain gauge at the top of this beam and the bottom of this beam, that the strain response would be proportional to both the axial force and also the bending moment. So you could really think about then, we could work backwards to figure out the forces and moments being carried by this structure are related to various combinations, in this case linear combinations, of these two strain gauges. The difference of the two strain gauges helps us understand bending. The average of the two strains helps us understand the axial force. So really we can work backwards from this. This is how a load cell honestly works, is we can turn this all around and think about this in terms of some kind of a system of equations. The strain at the top and the strain at the bottom are functions of geometry and also applied loading. So what I'm trying to do here is just indicate to you mathematically how the concept of inputs and response can be thought of as a system of linear equations. Now, a system of linear equations is nice to look at this way, but when we get a lot of equations, then we might look at this in matrix form instead. So really, we can take that input and response system and think about it as a series of linear equations in matrix form. So we can see right here that the strain output is a function of geometry and such, and also the applied loads. So this matrix A that I've got in the middle of the screen here is really based on geometry. And you can imagine with simple geometries, you can define this relationship with geometry just based on simple hand calculations, P over A, My over I, various moments of inertia and such like and whatnot are easy to calculate. Or you could think about this analytically speaking. If the geometry is a little bit more complicated, we could think about that as being the finite element response, right? The influence of a unit load. How does a unit load become a strain? So ultimately, the reason why we're trying to do this is to get to the highlighted equation at the bottom. If we know how load and strain are related, either from back of the envelope calculations, hand calcs, or by using finite element analysis, we can then invert that strain sensitivity matrix. So here's its inverse, which means then if we have measured strains, we can do this algebra on it. This is just linear algebra and matrix inversion and such to calculate the forces that would have caused those strains. So the key concept here is that measured strains in geometry can help us get back to the forces and the moments that were applied. Now this is pretty easy. This matrix, the strain sensitivity matrix, is really pretty easy, as you can see up at the top here, if we're working with simple geometry. But the challenge is what happens if we're building things that are actually used. So we talked a lot about cantilever beams and thick-walled sections and whatnot in college. In reality, we end up with something that's far more usable to a customer, therefore will keep us employed, and it looks something like this. So that strain sensitivity matrix may be very difficult for us to arrive at based on hand calculations. So how then could we back calculate the loads on this from measured strains if the geometry is complicated? Well, that raises the question just like probably a lot of you guys have thought about. If you have a complicated structure, how do we figure out how much stress results from load applied to it? That's what we use FEA for. So finite element analysis is a powerful tool that we're going to leverage here. So we're going to use the idea of structural response as a linear function of input loads to our advantage. As a matter of fact, FEA can help us with this understanding of how does load become stress. So really, you can think about it, if we had a couple of strain gauges on this part and we loaded it in a couple degrees of freedom, we have L1 in one direction, we have a load 2 up at the top in another direction. You can probably imagine that let's estimate that the structural response is a linear function of all those loads. So we can really think about this as a series of linear equations. Strain gauge 1's response is some function of load 1 and load 2, so on and so forth. So we can, again, now think about this in matrix form. So here's our friend, the strain gauge sensitivity matrix, A. We saw that green square earlier, and here it is again. It's going to come back and revisit us a couple times here as a way of just trying to keep in mind of mathematically how we're doing this. And realistically, something to keep in mind right now is that strain gauge sensitivity matrix will come from finite element analysis, and I'll show you what that looks like in just a minute. That raises the question, though, of if we want to have a good way of understanding what load 1 and load 2 are, or any of the loads are applied to the structure, where should those strain gauges go? At the very least, we need as many strain gauges as loads, right? So we're certainly not going to learn about the difference between load 1 and load 2 with one single strain gauge. We'll need at least 2, and it may help improve the precision of our calculation by including more than the degrees of freedom of loading. Maybe additional strain gauges will help. So that raises the question of where should the strain gauges be, and in what orientation should they be, and how many of them should we have? So these gauges could really be placed anywhere on the part, in any orientation, but optimally speaking, there's probably some locations that are better than others, and orientations that are better than others. So we call this the strain gauge positioning part of this exercise. So we need at least as many gauges as we have degrees of freedom of loading. The orientation and location will affect the precision of our calculation. So we need then a method of picking a gauge set, orientations and locations, that will be most precise in its ability to calculate load. So we're going to use, inside nCode DesignLife in just a minute, we're going to see this concept of the virtual strain gauge. So the virtual strain gauge has been around inside nCode for a while. Its goal in life is to recover stresses and strains in user-specified locations and orientations such that we can compare with actual measured strain data. Okay, so this is often used as a correlation tool to see how well does my finite element model predict stresses and strains relative to measured stresses, measured strains, or calculated stresses from measured strain gauge data. So we've had other seminars, webinars in this series talking about the correlation of finite element models with measured strain data. And the virtual strain gauge is a hugely important tool to use in that exercise. And you can see that in the red and the blue lines over on the right side here. Analytically derived stresses versus measured stresses or strains. What we're going to use today, though, is not to do this as a correlation exercise, but we're going to use it to back calculate loads. So we're going to use the concept of the virtual strain gauge to back calculate loads. Okay, and I'll show you how we do this in concept in just a couple slides here, and then we'll look at this actually in detail in a demonstration just a bit. So here's the virtual strain gauge. A number of you guys have probably used this before. The idea is that in a finite element model inside nCode DesignLife, I can choose locations to put strain gauges, different orientations and such, and then based on loading that's applied and some material properties, I can recover stresses or strains. Now the key thing is that if you get this right, if you do this right, essentially we can come up with how much strain is there in each location as a function of input load. Why do we care about that? So we can recognize this green square again. Here's the strain gauge sensitivity matrix again, right? We said before that the key thing that ties together loading to structural response is geometry, in this case a finite element solution. It's the strain gauge sensitivity matrix. It just happens to be transposed in this case. But this is a key piece of information that helps us understand either how does load become strain, or to be very specific today, what we want to do is turn that around to figure out what loads would have caused these strains. Let's reconstruct the loads that caused measured strains. And this is the key linchpin to all this, is this structural response using a finite element model and these things called virtual strain gauges. So with the ability then to understand this relationship between structural response in load input or vice versa, how does load become stress or strain, that means we can then use this process of load reconstruction. And you'll see this live in just a minute inside nCode. Here we have a finite element model. The beauty of that is that gives us the strain sensitivity matrix. There's that green square again. That's the strain sensitivity matrix. Down at the bottom here, these are the measured strains. So for the locations in the field, we measured strain gauge data. We've calculated inside DesignLife now using FEA and DesignLife's virtual strain gauge glyph. We've calculated the strain sensitivity matrix, which means now I can use this loads reconstruction glyph to calculate what are the loads that would have caused these strains. So graphically speaking, visually, this is the loads reconstruction process. Understanding of FEA, measured strains, allows us to back calculate these loads. Now the loads here, this is a kind of a matrix form. We've got this L hat, L for load, hat for estimate. So this is just our reminder that we're estimating these loads, and the fidelity of this estimate, or the precision of this estimate, will be dependent on what gauge, really on the quality of the strain gauge data that comes in. So that raises the question of what's the proper way to select strain gauge location and orientation. So I'm going to address these two questions throughout this webinar today. Where should the gauges go? And then second, once we've done that and measured strains in those locations, how do we calculate those loads then with some measure of precision. So the whole process looks like this. How do we capture or predict these loads that have enduring value that we can use in the next generation redesign? Step one, we got to figure out where the strain gauges go. I'll show you how this works in just a minute. This will rely on what we call a gauge positioning analysis inside DesignLife. Then we go off and measure strain gauge surface data. Okay, so we take those locations, those orientations, and apply strain gauges to our actual part, or we provide this detail to test engineers or mechanics that are good at working with these small strain gauges. This is not trivial to go measure strain gauge data, but it's something that a lot of people have been doing for a very long time. And then lastly, we can use that strain gauge data to reconstruct the loads that cause those measured strains. So really 3 steps. 1 is figure out where should gauges go. Step 2 is measure strain gauge data. Step 3 is reconstruct the loads. And I'm going to focus today on how to do steps 1 and 3. So I'm not going to get into the detail of how do we actually measure strain data in the field. That's a bit out of this topic here. But HBM as a company has all kinds of beautiful strain gauges and data acquisition hardware, robust field data acquisition units, and so on that will help in step 2. I'm going to focus on steps 1 and 3 now going forward. So step 1 was where should the strain gauges go? Let's talk about this in concept before we look at it in detail. We have a new glyph in nCode 11 called strain gauge positioning. And this will help us understand where should strain gauges go for the highest precision of load estimate. This is based on a PhD thesis by my colleague Mary Wickham that was trying to, essentially she pioneered this concept of using these, calculating load estimates based on linear algebra matrix math, looking at that strain gauge sensitivity matrix. So that strain gauge positioning glyph, its methodology is we're trying to come up with that strain sensitivity matrix. There it is again, the green square. Trying to come up with a green square that best estimates loads. So highest precision of estimated loads. And I should probably explain, why do I keep saying estimated loads? That's because there's noise or uncertainty inherent in any measured parameter, including strain. So you'll see later on when we use this calculation approach, you'll see that one of the input parameters is typically how much strain gauge noise is there, how much uncertainty is there in strains. And we can see how that then influences our load estimates. We'll get like plus or minus 1 standard deviation in our estimates. So really we're trying to come up with strain gauge locations that will do the best at minimizing that variance, or conversely maximizing the precision. Of course, our friend the green square here, the strain gauge sensitivity matrix, will be its ability to predict loads. Its precision will be influenced by the number of gauges, location of gauges, and orientation of gauges. So we have now inside the strain gauge positioning glyph an algorithm that works through these 5 steps to find the best place for gauges. So first off, look on the surface. Why? Well, it's because strain gauges have to go on the surface. Second, exclude any user-specified nodes. So there may be certain areas where we just can't put a gauge based on geometry, based on size, something like that. Third, exclude nodes with hard edges. So you can see here we have some fillets, we have some edges, that kind of thing. We're obviously not going to put strain gauges on bent surfaces, so the algorithm will ignore those. Fourth, exclude nodes with a small radius of curvature. So kind of the opposite of the hard edges thing is look for areas with a radius below some user-specified value and ignore those. Typically speaking, we want to get strain gauges in areas of high strain, but not right in notches or radii, because we end up with problems with gauge orientation, gauge averaging in areas of very high stress gradients. As a result then, this glyph, this strain gauge positioning glyph, then has this candidate set of all these black nodes here where gauges could possibly go. And it'll work through and figure out where could those gauges go then. Say if I said we need to look at several different loads here, what are the best places to mathematically to increase the determinant of the strain gauge sensitivity matrix A, or to put it a different way, to increase the precision, reduce the variability in the load estimate. So let me just show you what this looks like. We'll jump over here into nCode. So give me just a second here. I need to share my screen for you this way as well. So just a second here. And I hope you can see nCode now. Okay. So this is nCode 11. I assume a number of you guys have used this before. If you haven't, this is a pretty deep dive technical topic today. If you take a look at previous archived webinars on ncode.com, you'll find some that are much higher level at what is nCode, how do we get around inside this at all. Now I've got my workspace set up maybe a little bit differently than yours. I've put the available data window and the glyph palette together on top of each other just to make the most of this screen space over here. So I'm going to go open up the process now. And rather than building a process from scratch, I'm going to use this, what we call a flow, like a flow chart. This is a template or process I built earlier called string gauge positioning. Go ahead and open that up. And what we have here is, here's our new string gauge positioning glyph. So pretty simple process, 3 glyphs. I have my finite element model here that I need to go grab. Let's go put this one in here. And let's just take a quick look. This is not very exciting geometry, I'll admit that, but it will save time today in terms of running quickly. And we'll file this under learning to walk rather than let's get started running. So in terms of degrees of freedom of loading on this thing, we've got, I've solved this, I've done a unit load input for 4 separate degrees of freedom of loading. So I've sat down and maybe reviewed with the design engineer, with product people, with structural analysts, whatever. How is this thing loaded in real life? And it's actually, there are 4 ways it's loaded. So 4 degrees of freedom of loading. So this one's pretty simple. This is an axial load. Okay, so that's one way it's loaded. It's held here and pushed over here. Here's another one. 2nd degree of freedom of loading is torsional case. 3rd one is bending, and you can see this would be bending on the z-axis, just based on the contour plot here. And then lastly, bending on the y-axis. So 4 degrees of freedom of loading here, and this raises the question then of if we want to understand what those 4 loads look like in service versus time, remember 3 steps to this. If we want to figure out an estimate of loads, number 1, we need to figure out where strain gauges should go. Number 2, we need to measure that strain gauge data. Number 3, we need to do the back calculation to figure out what the loads are from the measured strains. So let's do this one step at a time. We're going to use the strain gauge positioning glyph here to help us understand where should gauges go. Now in terms of properties, let's just go take a quick look here. We have a couple of properties here that allow us to indicate candidate gauge locations. So for example, down here I've said I want to look at using up to a maximum of 6 gauges. I've got 4 degrees of freedom of loading, so I need at least 4 strain gauges, but I want to look at 4 and also possibly using 5 strain gauges and also possibly using 6 strain gauges, because using more may improve the precision of my calculation. We also have some information here about signal noise, so how sensitive are these strains, and you'll see that plays out in a little bit. Excuse me. Feature angle, nodes to exclude. These are all, I had a slide earlier that said gauge candidate locations are based on a lot of things based on geometry and such. So these are just questions that I can answer to try to help to specify, stay out of areas of small radii where boundary conditions are, that kind of thing. So not a whole lot of craziness going on inside that calculation. So let's just go ahead and run this. It's going to run, and it actually runs an optimizer trying to maximize the determinant of our green square friend, the strain gauge sensitivity matrix. And in the end, it gives me 4 answers. It says we have 4 possible ways we could put these strain gauges on. We could use 4 gauges, we could use 5 gauges, or we could use 6 gauges. And then over here are some statistics of how useful those gauge sets might be. We have a determinant, so this column number 2 is the determinant of the green square matrix. I shouldn't say square because it is not necessarily a square matrix, but graphically I've been showing it as a green square, the strain gauge sensitivity matrix. We also have some variance parameters. Off to the right here, we have VIF. This is called variance inflation factor. This has to do with collinearity of loading. So the lower these numbers are, the better. So get some interesting, very interesting statistics here. And to be honest, some of these statistics come outside of the world of engineering. They actually come from the world of medical tests in statistics, of trying to look at the influence of one parameter on another, or influence of a series of parameters on one output variable. So I'm not going to dig in depth into what this VIF, or variance inflation factor, is today, but that's something that you guys can take a look online if you want. So it says here we have 3 different ways we could put gauges on here: 4 gauges, 5 gauges, or 6 gauges. So let's go back in here and see where those are. So I'm going to go ahead up here to the virtual strain gauge. Now, some of you guys may have used this before for correlation. I can pick a spot to put a gauge, but actually the picking has already been done for me by the strain gauge positioning glyph. So I want to import those results, and I want to bring in this candidate set called 6 active strain gauges. So candidate set with using 6 gauges. Open this up, and what I have here now is, let's just take a look over here. Zoom in here a little bit better. We can see what's going on, and we have a series of strain gauges. So 1, 2, 3, 4, 5, 6. So those are 6 gauges right here. Let's take a little bit closer look here. Right, so we have six strain gauges, and you can see the location of them has been chosen to be sensitive to those 4 different degrees of freedom of loading, right? So you can imagine we have gauges at the top and bottom surfaces to look at bending. Their differences will help us understand bending on different axes. Their averages will help us understand axial loading. So not too hard to figure out why gauges are in certain spots. Now you may wonder, why do we have 2 gauges on top of each other right here? This is really just saying we need to put a rosette there. This is saying this area right here is very sensitive. It's actually probably trying to pick up the torsional load case, right? Because the difference between these 2 different orientations in this location, the shear, will help us understand how much torsion there is. So you might look at this and say, okay, how are we going to do that with 2 strain gauges right there? I would just put a rosette there, and then look at those two directions. Okay, so now step 1, again, the whole process, if we want to figure out what loads are like passing through our structure, step 1, figure out where to put gauges. Step 2, go record that strain data. Step 3, back calculate the loads from the measured strain data. So we're still focusing on step 1, which was where should the gauges go. Here we have a candidate set of, we could put 6 strain gauges in these spots. I think realistically, no one will stop at this point. Most typically, there's some kind of iteration to be done where I might say, you know what, I can't put a gauge there, or, we have to put a gauge over here instead, or otherwise no one will believe me. Maybe I have some other reasons. We already have a strain gauge over here, so that kind of thing. And there are various degrees of interactivity in here that we can use. For example, I could use the same strain gauge positioning, the virtual strain gauge tool here, to add a strain gauge and say, you know what, I want to put a strain gauge over here myself, and then rerun the calculation of strain gauge positioning, requiring the strain gauge positioning glyph to use what I've just placed myself. So there are degrees of manual intervention that will come into play here. Gauges that I put on myself will be required to be part of the solution set, which means then I can have not just 6 gauges that mathematically make sense, but I could pick out 1 or 2 locations myself and then add to it 4 or 5 others that mathematically make sense. So this is, usually there's some kind of an iterative process to this. But again, the goal here was to calculate, or to gain insight into the orientation and the location of those strain gauge positions. All right, so that's step 1. Step 2, go record that strain gauge data. So again, that's not trivial, but fortunately HBM provides all kinds of cool hardware for that step in the process. They produce all kinds of strain gauges, data acquisition devices, and so on. So let's say then that the test engineers go out and measure all that measured strain gauge data. So step 2 is done, and now we're going to progress on to step 3, which was how can we estimate the loads from those gauge locations measured strains? So at this point, I'm going to leave that process, and I'm going to use a different process now, which is called load reconstruction. Okay, so this process has a few more glyphs to it. Mathematically, it's similar in concept. It's based on some matrix math. So down in here, this is going to be some matrix math. Remember before we said that loads and strains are related by a strain gauge response matrix, strain gauge sensitivity matrix. We did our best to optimize that strain gauge sensitivity matrix in step 1. And now we're going to use that strain gauge sensitivity matrix in step 3 here so that we can calculate loads. So we got the model. That goes back up here. Again, same model as before. Okay. So in this model, we have 4 degrees of freedom of loading. Notice, though, that I've got those strain gauges on here this time. Okay. So like we had seen before, let's just zoom in here, take a little better look. Like we had seen before, we have those gauges. How do those come in here? Well, there's an import mechanism that I can say, I want to import strain gauges. We saw this before in just trying to review what are the 6 strain gauge locations that, that mathematically make the most sense. So anyway, so now we have the same model in the gauge set like we had seen before. And then down here, these are our measured strains. So let's just go take a quick look at these. So this is measured strain gauge data. Here it is. So we have 1, 2, 3, 4, 5, 6 strain gauge histories, all measured versus time. So this is the result of what we called step 2 previously. Go measure that field service strain history data. Okay. So mathematically, think about this again. Back to our matrix form. We have measured strains. We have we are capable of calculating from finite element analysis what is the strain gauge sensitivity matrix, and now we just need to use that in this loads reconstruction glyph to back calculate loads. Let's go ahead and run this and see what we get. It's going to take a little bit longer to run because it's got to work through a lot of time series data this time. It's got some matrix inversion going on inside that load reconstruction glyph and such. So when this is finished, what we'll find is that we'll have computed loads as a function of time. Okay, so first off, up at the top here, this right here, this table of data, this is the strain sensitivity matrix, the green square. And to be specific, this is the transpose of it. But the idea is that this is from the unit load FE that we did up here. So the unit load FE and the virtual strain gauges we've placed on the model, what's the output strain as a function of input unit load. And of course, with the measured load down at the bottom, we can measured strain, excuse me, at the bottom, we can calculate then an estimate of what loads would have caused these strains. And that is shown right here. So let's take a closer look at this. What we've got is in red, this is the measured load for load degree of freedom number 1. Remember, in our case, we had 4 degrees of freedom of loading. We had axial, torsions, MZ, and MY. So 2 bending moments, torsion, and axial. So this is the load history as a function of time for the first degree of freedom of loading, and then of course also for the second. So this is the torsion, and this is the MZ, and this is the MY. These are all given as functions of time. The gray squiggly lines at the top and the bottom are plus or minus 1 sigma. So this is a record or an estimate of variability. You may wonder, where does variability come into play here? We have measured strain gauge data, that's deterministic. We have a finite element model, which produces deterministic structural response. So wherever does variance come into play here? So let me just show you here. Either in the load reconstruction glyph, or someone has set up a glyph here called setup parameters. If we just look in the properties here, one of the input parameters is what's the error on the strain. Okay, so what's the uncertainty on the strain? In other words, when the test engineer measured strain gauge data, we'll have electrical noise or some type of variability, uncertainty, just in measurement quantification error, you could call this. How large is that? So nCode as a piece of software doesn't know that. This is a required input by you, a user. But you can estimate this just by looking at measured strain gauge data, for example. You could look at measuring strain gauge data when the part is not in use. So when the vehicle's turned on, when the aircraft is sitting on the runway, when the phone is turned on but not being used, what's the squiggliness, you could say, the variability in the strain response, and I can use that here. So now we're introducing a probabilistic side of things here, or introducing a variable into the system. And depending on how well conditioned this strain gauge sensitivity matrix is up here, depending on how precise its capability is to understand degrees of freedom of loading as in strains, that cascades through then into making up plots like this, where we can quantify this variability. So we have plus or minus 1 sigma being shown here in these kind of ghostly gray lines at the top and the bottom. So if, for example, if we were to do this analysis with a reduced number of strain gauges, we had 4 degrees of freedom, so we need at least 4 strain gauges. But using more may reduce variability or increase precision. If we were to use 4 strain gauges instead of 6, we'd probably find that the variability would be increased here. We could see that very quickly graphically in this plot. We could also see it very quickly over here in this. This is a metadata display that just says what's the variability on each load. We could also see it in some of these other terms that we looked at earlier, like the strain gauge sensitivity matrix. There's a thing called the VIF, the variance inflation factor, that said how collinear are the loads if we use this this strain gauge sensitivity matrix. So we have various metrics built into this calculation, so we can look at this in not just a deterministic way, but in a probabilistic way, because we know that we have variability in measured strains. Last thing to show is down at the bottom. This is just, you could say, doing a back calculation on the back calculation. So we were back calculating from strains into load, and this is now going one step past that to say how well does this, from the measured load, or excuse me, from the estimated loads, what do the strains look like from that? So in other words, measured strains became estimated loads. Well, estimated loads on the model can give us estimated strains. So this is just tying that loop back together again to look at just how viable are these estimates. If you look at these separately, you can see they look very similar. If we put them on top of each other, you actually can't even see the other one. So this is just another way of trying to prove to ourselves, does the calculation I've done here make any sense, or have I missed something along the way? So this is the general process we're looking at. Again, 3 steps where, first off, where should gauges go? And that's using the strain gauge positioning glyph, which is, by the way, new to nCode 11. So here it is right here, strain gauge positioning. That's new in nCode 11. That was step 1. Step 2 was record measured strain data. And step 3 was then reconstruct an estimate of the loads that would have caused those strains. And that's using the load reconstruction glyph, which has actually been available inside nCode now for about a year or 2. So we'll do a question and answer session in just a minute here. Before we do that, one other resource I want to point out to you is if you go down into the manuals in the lower left here, and then go to the DesignLife work examples. Some of you guys probably have seen this. If you haven't, this is an awesome resource to learn about how do I do things inside nCode. Okay, so here is the DesignLife work examples in PDF form. It's got 25 chapters, how to do 25 different things. Some of these are other webinar topics we've talked about in the past, like how to deal with welded structures, how to look at vibration fatigue, the influence of temperature, and so on. The one I want to point out to you guys today is the load reconstruction one, which is completely skipping. Yeah, here we go, load reconstruction example number 20. And this is just a step-by-step tutorial to really show you how I did what I did today. So I probably should have mentioned this first off. You don't need to take feverish notes or try to remember everything I've done. This resource here will step you through. Hey, look at that. Recognize that process? That's the exact one we just used. So this will be this is a great resource for you guys to go off if you want to reproduce what we've done here today. So let me just summarize here what we've done, and then we'll open it up for question and answers. So in summary, what have we talked about here? So what did we just talk about? Good question. Strain gauge measurements can help us understand loads, okay? Finite element analysis came into being to help us understand how we could get away from using strain gauge data, right? Traditionally, finite element analysis helps us go from load into stress or strain. But now, if we're smart, we can turn this around and we can use this component as its own load transducer. So work backwards. Use the finite element results and measured strain gauge data to work backwards to estimate loads. So this is cool because we can then predict load without modifying the part, so we don't have to change the design. We don't have to add a load cell. Now, there will always be reasons to use load cells, custom force transducers, and so on. I'm just providing today essentially another tool in your engineering toolkit. This is good then because we're not limited by traditional transducer design. Here's a very interesting one. We can take advantage of crosstalk. So in the geometries we've looked at today, simple blocky things, it's pretty easy to figure out where strain gauges should go to best estimate loads. In real geometries, that can be much harder, and it can be a real challenge to try to manually separate, mathematically separate, one degree of freedom of loading from another. We don't need to separate degrees of freedom of loading using this approach. The strain gauge sensitivity matrix tells us that. If there's crosstalk, if one load causes strains in two different locations and another load causes strains in different locations, that's fine, that's crosstalk. We have one input causing several responses. It's the difference in responses from different loads that will help us. So crosstalk in the strain sensitivity matrix will be accounted for. With typical transducer design, crosstalk is the enemy of precision. Mathematically, as long as we account for it, as long as your model can understand it, it'll be in the strain gauge sensitivity matrix, and it'll be used to minimize the error or the variability in our load estimates. Why do we do all this? Because load histories have enduring value, and we can use loads in the next design. So that's our overall goal here, is how do we get access to load data when traditional load cells may not help? How do we get access to that load data? So just as a reminder, work example number 20 in DesignLife will help you understand this. This is something you can reproduce. Anywhere nCode is installed, you'll find these worked examples. This is a great resource for learning more. So with that, I'll turn it over to you guys, and we'll start